In the majestic Andes Mountains of South America, engineers are forced to split sheer cliffs to build massive roadways under conditions so extreme that even the smallest miscalculation can send an entire project sliding into ravines hundreds of meters deep. Through millimeter-level calculations, precisely controlled drilling and blasting, and the use of heavy machinery weighing hundreds of tons while clinging to steep mountain slopes, engineers have managed to carve winding roads that trace the UE mountainsides like steel threads. These roads reconnect regions that were isolated for centuries, turning once impossible terrain into lifelines of transportation. In the Andes, road construction is not simply an engineering task. It is a direct confrontation with gravity, geology, and some of the harshest natural conditions on Earth. Many highways in Peru, Chile, and Bolivia are constructed at elevations ranging from 3,000 to 4,500 meters above sea level, where thin air can reduce human labor efficiency by 30 to 40%. Weather conditions can shift dramatically within hours, changing from intense sunlight to freezing winds or sudden snowfall. In these environments, more than 6% of total project costs are not spent on pavement or asphalt, but on rock excavation, slope stabilization, and landslide prevention alone. To manage these challenges, mountain roads in the Andes are generally built in two main stages. The first stage involves cutting the road directly into the outer cliff face, stabilizing the slope with anchors and retaining structures, and protecting the roadway from falling rock. When terrain becomes too steep or unstable, construction shifts to the second stage, tunneling through the mountain to bypass the most dangerous sections while reducing exposure to landslides and extreme weather. The construction process begins long before any rock is removed. Engineers precisely determine the road's centerline and mark construction boundaries directly onto the exposed rock face. Based on this layout, drill holes are arranged according to pre-calculated blasting plans. Explosives are carefully loaded in controlled quantities to fracture the rock in segments, ensuring that the overall stability of the mountain is not compromised. After each blast, excavators move in to remove the fragmented rock and soil, gradually clearing the construction surface. This material is loaded onto heavy-duty trucks positioned along the edge of the road, which operate continuously along temporary access routes to haul debris to designated disposal areas. In some sections where terrain allows, bulldozers push material directly down steep slopes or into riverbeds below, significantly shortening clearance time. Once excavation is complete, bulldozers shape the road by pushing and trimming material to form the initial roadbed. Operators constantly adjust the blade angle to achieve the required slope and elevation, creating a rough but stable surface for subsequent work. The cycle of drilling, blasting, excavating, bulldozing, and grading is repeated section by section until a continuous roadway begins to emerge, firmly anchored to the cliff face. After the ground has been leveled and stabilized, graded aggregate or crushed stone is delivered by trucks and dumped along the alignment. Wheel loaders redistribute the material evenly, preparing it for compaction. Motor graders then spread the material into uniform layers, adjusting elevation and cross-slope, precisely according to design specifications. Water trucks spray the surface to control dust and create optimal moisture conditions for compaction. Vibratory rollers or steel-wheeled rollers compact each layer through multiple overlapping passes to achieve the required density. In curved sections or areas near the cliff edge, graders continue refining the road shape to ensure proper drainage. In narrow zones where heavy rollers cannot operate, workers use hand-operated compactors to ensure uniform density and prevent localized settlement. Every step is carefully monitored, as uneven compaction or slight misalignment can compromise long-term stability. Meanwhile, slope stabilization continues above the roadway. Workers secure themselves with safety harnesses and climb the steep rock face to access unstable sections directly. Using pneumatic drills, they bore into protruding rock formations, breaking off loose blocks and flattening the slope. This work is performed slowly and methodically, with constant assessments of rock cohesion to prevent sudden collapses. Throughout these operations, workers wear full protective equipment, including helmets, harnesses, masks, and gloves. Once stabilization is complete, the entire cliff face is often covered with steel mesh to secure loose fragments and significantly reduce the risk of rockfalls onto the road below. The next major phase is asphalt paving. Before laying the surface layer, workers spray a thin coat of liquid asphalt onto the compacted roadbed to ensure proper bonding between layers. This coat is heated using gas burners, allowing solvents to evaporate and activating the asphalt's adhesive properties. During paving, the asphalt paver moves slowly along the road, continuously receiving hot mix from dump trucks feeding into its hopper. The heated screed spreads the asphalt into a smooth, continuous layer, while workers on either side monitor edges and manually correct imperfections near shoulders and curves. Heat and smoke rising from the pavement indicate the high working temperature, requiring precise timing and coordination. A continuous black ribbon of asphalt gradually forms, marking one of the most visible stages of completion. After paving, high-pressure sprayers clean the surface of loose material, ensuring proper bonding and surface quality. As the asphalt cools, it hardens into a solid, continuous roadway that follows the mountainside's natural curves. From above, the finished road appears like a dark ribbon draped across the cliff, symbolizing the completion of an engineering feat achieved under extreme conditions. In areas where the cliff face is nearly vertical and there is no space left to excavate, engineers adopt a different strategy. Instead of cutting deeper into the mountain, the road is suspended along the cliff using reinforced concrete columns and prefabricated modular sections. Massive columns are anchored directly into bedrock, forming the structural backbone of the roadway. Materials are delivered using cranes or specialized transport systems, often lowered from above. Once the columns reach full strength, prefabricated road deck modules are installed section by section, much like assembling giant building blocks. Each module includes steel girders, concrete slabs, and connection points, reducing on-site construction time. As modules are secured, a continuous roadway gradually takes shape along the mountainside, followed by installation of safety barriers, drainage systems, and surface finishing. When neither cliffside construction nor elevated structures are feasible, engineers turn to tunneling directly through the mountain. The project begins with the creation of a complex ventilation system, as air quality deep underground can become toxic within minutes. Vertical shafts 4 to 6 meters wide and up to 200 meters deep are drilled to supply fresh air and expel exhaust. Sensors continuously monitor oxygen levels, temperature, and gas concentrations, while powerful jet fans regulate airflow. These shafts are constructed using raise boring techniques with extreme precision, forming the respiratory system of the tunnel. Deep underground, the tunnel boring machine is assembled piece by piece. Hundreds of transport vehicles deliver massive components, including the cutter head weighing hundreds of tons and nearly 15 meters in diameter. Auxiliary tunnels are widened and reinforced to accommodate assembly. Using laser guidance with millimeter-level tolerance, engineers align and connect each module. Once fully assembled, the machine stretches nearly 100 meters long and weighs thousands of tons. When activated, hydraulic systems drive the cutter head into solid rock with immense force, while rotating alloy discs crush the stone. Each cycle advances the machine roughly 1.2 meters, repeating continuously day and night. Crushed rock is removed by conveyor systems, and high-pressure water cools the cutting head. After excavation, the tunnel undergoes exhaustive inspection. Engineers use pressure sensors, ground-penetrating radar, ultrasound, and high-resolution optical systems to detect even microscopic defects. Ventilation systems, drainage pumps, fire safety networks, and backup power supplies are tested under strict international standards. Only after every parameter meets design requirements is the tunnel declared complete, representing the final triumph of precision engineering and human resilience beneath the mountain. From clinging to mere vertical cliffs to suspending roadways in midair and drilling through the heart of the Andes themselves, these projects demonstrate how modern engineering adapts to the planet's most unforgiving landscapes. Each road stands as a testament to determination, innovation, and the relentless pursuit of connection across the world's most extreme terrain.